C'est moi qui t'appelle.
Ça me paraissait évident qu'il y avait un problème.
C'est moi qui t'appelle. J'ai plus le courage de monter. Donc il est connecté. Il
non, mais parce qu'il manque la zénith. Ah, bien. On a pas USB. Ça, c'est USB.
Pardon.
Le câble HDMI.
Donc en fait, les gens avec les orations qui sont pas là,
c'est bon.
Il y en a plein qui ne vont pas venir. Le jour de la conférence, dans la troisième semaine, ils vont venir déjà.
La conférence, moi j'espère que les Allemands viennent. Lui, par exemple. Ok. Very good. Wonderful.
Can you see this?
Yeah, right.
Okay, so let me first do something else. 1 second. I'll post my lecture notes to the chat.
Yeah. Il n'y a pas de caméra qui filme ça.
C'est correct, mais en fait, tout le. La vidéo.
Ah oui.
Somehow it does not work. Do you know how recently I did this and I could just share it directly?
Je dis, j'espère que personne ne va se braquer. Ah, ça nous manque un petit peu. Voilà.
Une présentation. J'ai plus de zoom. So we wait for 1 more minute?
Yeah, good.
One or two.
Yeah, perfect.
Tu arrives à accéder à la salle de jeu? Tu arrives à accéder à la salle de jeu?
Yes.
You succeeded. Okay. Ah, okay. Here it is. Well, I can.
Yeah.
Déjà 32, 34. Okay, Felix, are you okay?
Yeah.
Okay. So it's a pleasure to introduce Felix Schulze from University of Warwick. Am I right? Warwick,
Yes.
And he'll talk about the mean curvature flow and variation around this thing. Please.
Okay. Laurent Gérard, thank you very much for the invitation to give this this mini course here. Yeah, it's very nice to do that. And yeah, I'll give an introduction to weak solutions to mean curvature flow. And first, don't hesitate to interrupt me if you have questions. Yeah? So I'm happy to answer questions. I've also typed lecture notes where I put the link, a Dropbox link, into the Zoom chat. So you can click the link and download the notes. The notes are quite a bit more extensive than what I'm doing here in the lectures. I'm giving quite a bit more details there. Also a bit more introduction for people who have missing maybe a little bit more of the differential geometry background. Yeah. So this, what I'll be doing in the lectures here now, is a bit, in some sense, a compressed form, at least sort of in the beginning of what is in the lecture notes. So please have a look there as well. So the main idea here is to give sort of an overview about Brakke flows. Is sort of one way to define weak solutions for mean curvature flow. I will in the very end of the course also relate Brakke flows to level set flow and explain sort of what the connections are. So the main thrust in the beginning of these lectures will be to give a compactness theorem for Brakke flows. And we will see that having compactness gives us actually also existence. For anyone more interested or who knows maybe does more Ricci flow, this theory of Brakke flows is more or less parallel to what Richard Bumler has recently introduced for Ricci flow. So what Richard has done now is more or less build up the theory that you can speak about weak solutions for Ricci flow. You get under very natural conditions, get compactness. And so if you have seen part of that thing and haven't seen Brakke flows yet, you'll see a lot of parallels. There are a lot of parallels. And in Brakke flows, since you have an ambient space, a lot of things are much easier. But you can, for example, here see for Brakke flows, by having a good compactness properties, we can produce existence. This is usually like in normal PDE theory, variational problems. If you have good compactness, you can go to weaker spaces, and then suddenly you can construct solutions where without these compactness properties, you wouldn't be able to do this. Okay, now, so today, what I'll try to cover today here is I'll give an introduction to smooth mean curvature flow, the very basic properties. I'll be rather brief on that. There's much more about this in the lecture notes. Then, since we will later need to talk about weak compactness for mean curvature flows, we need to first talk about weak compactness for submanifolds. So if you have a submanifold in Euclidean space, or more generally in a Riemannian manifold, and what we'll assume is bounds in the first variation, i.e. an integral bound on the mean curvature, sort of what do we know, what kind of compactness can we expect? That would be similar for Riemannian manifolds, that you go to metric spaces and you take sort of compactness as a metric space, and your space could look much weaker in the limit, but at least you can find a limit. And after doing this, I will define Brakke flows today and discuss their basic properties. And so tomorrow, I'll say something in the end what I'll do tomorrow. Tomorrow will be sort of the main compactness theorem and then further applications in existence. Okay. Now, so what is mean curvature flow? Okay, so the classical setup, if you have a closed n-dimensional manifold, you have a smooth family of immersions. Just for simplicity, just do it in Rn+1. Also, if you don't want to take notes, I will put a copy of these notes into this Dropbox folder, so you can access them tomorrow or later. So these are the moving surfaces. Then you say that MT solves mean curvature flow. If the following evolution equation is satisfied, if you take the speed of the solution, but you only project it to the normal space at each point, that this is given by the mean curvature vector. Since we're in codimension 1, we can also write it as mean curvature times a choice of unit normal vector, where mean curvature is just the trace of the second fundamental form or the sum of the principal curvatures. So that's why it's mean curvature. And since it's a parabolic problem, this is, you have to specify the initial immersion or embedding. Okay, and so what are examples here? The very basic example, which I guess you've seen, or you have shrinking spheres. So an n-dimensional sphere of radius r of t, centered at any point p, where the radius at time t is just given by r0 squared minus 2nt. So what do we see here? So the initial radius is r0, and we see in finite time at t capital at the final time is capital R0 squared divided by 2n. the sphere will contract to a point. Yeah? And we see curvatures blow up as the sphere contracts to a point. Now you can then take products and still get a solution to a mean curvature force. You have then shrinking cylinders. So you have these generalized cylinders. You have SK with radius r of t at any point p times Rn minus k. And here the radius of t is just square root of R0 squared minus 2kt. Yeah. So these are all solutions to mean curvature flow. This is the very basic ones. Then one of the other fundamental ones, at least for curves in the plane, is the so-called Grim Reaper. Just to give a little tiny bit of a flavor, what there is. So this, you can look at the following curve. Y of x is minus the logarithm of cosine of x, where x lies between minus pi over 2 and pi over 2. Let's draw this here. So I'll draw the coordinate system in a bit of a weird way. So this is my y coordinate. This is my x coordinate. So here's minus pi over 2. Here's pi over 2. And then sort of the Grim Reaper sort of looks like this here. And that would be then, and what you get here, you get a solution which translates with speed 1 in this direction. Yeah. So if you let this flow by mean curvature flow, it doesn't change its shape. This just translates to the right. Yeah? So the important thing is to see this solution is an eternal solution. Eternal means it exists from time minus infinity to time plus infinity, because it's a translating solution. Yeah? And as I said, it's translating. Okay, they can, for example, but I won't go too much into other examples, but let's do one example. It's so-called paperclip. And there is an ancient solution of curve shortening flow, which looks for very large negative times as 2 copies of the Grim Reaper. We just glue them together, more or less. So you have to prove that this exists, but there actually is a closed formula for that, which looks like 2 copies of the Grim Reaper sort of translating towards each other. This gives an ancient solution to mean curvature flow. It's convex, so it exists for all negative times and then sort of disappears into a round point at some finite positive point or some finite time. Yeah. So this would be an ancient solution. So there are many interesting solutions. Now for curve shortening flows, the curve shortening flow is mean curvature flow in R2 of curves. Yeah. What are the basic theorems here? So the very fundamental theorem is the one of Gauge and Hamilton. 86, or Grace combined with the theorem of Grayson in 87, and says the following thing. So more or less for curve shortening flow, things are as nice as we can hope. So if you have curve shortening flow contracts simple closed curves in R2, 2 round points in finite time. So if you take an embedded closed curve, it will stay embedded and it will then shrink. And as it shrinks, it will contract to a point. And what means a round point is when you rescale around the final singularity, you'll see a small shrinking circle. So that's this contraction to a round point. And this happens in finite time. So this is really as nice as we get. So we see curve shortening flow really sort of uniformizes the shape for an embedded closed curve. We all, I guess, agree that the sort of the most symmetric shape for a closed embedded curve is a round circle. So it really sort of, while it forms the singularity, it really deforms the curve into sort of a canonical shape here. And now we can ask is sort of, is something like this still true in higher dimensions? So there's the corresponding theorem of Huysken, which sort of kicked off sort of this investigation in mean curvature flow. That actually before this result of Gauge and Hamilton-Grayson, mean curvature flow contracts, but in higher dimensions you need a curvature condition. You have to closed is okay, this is natural, but you need to assume convexity. Closed convex hypersurfaces in Rn plus 1 in finite time to round points. And I'll draw a picture in a moment when I explain a bit about. So it's a similar idea. Yeah? So you start with something convex. Yeah? Just think of the boundary of a compact closed convex set, and smooth, and then the flow will contract this hypersurface, will move it, will keep it convex, contract it to a point, and as you rescale around this final singularity, you see a shrinking sphere. Yeah? So this is kind of extremely nice, yeah? But you see, when convexity is the rather strong condition. Yeah? We understand convex surfaces hypersurfaces pretty well. There's not so much topology in there, not so interesting. So this doesn't give us so much of understanding. So one has to sort of extend a bit more what one looks at. So let's first discuss what the basic properties of mean curvature flow are. Now, if you have a general flow, a flow with just normal speed, if you just take minus f times nu, f is just our normal speed here, so which would be otherwise our mean curvature in our case. We can compute the first variation of area. So this is, I take this here as this is the area, the n-dimensional area of the surface. So this is just, if you write it differently, ddt of integrating just 1 over the hypersurface, then you get to this is in general integral f times h d mu t, where this is the measure at time t. Now you see, what do we get for mean curvature flow? So we get then for mean curvature flow, we get ddt mt is just minus integral mean curvature squared d mu t. What does this mean? So this is for mean curvature flow. This just means that mean curvature is the L2 gradient flow to the area functional. So it's the steepest descent with respect to the L2 measure, the L2 scalar product on the evolving surface. So in that sense, if we want to decrease the area of a hypersurface by a smooth family of surfaces, the fastest descent, or the steepest descent route is exactly going right in curvature flow. And you see also the stationary points are exactly minimal surfaces, which is a bit difficult in Rn because there are no compact minimal surfaces. So there won't be sort of any compact stationary points. Okay, now the next thing is here, there's more about all of this in these notes about this initial basic properties. We have smooth short time existence. So how does this follow? The idea is you can write the surfaces for a small time, mt, you can write them as a normal graph over the initial surface. Then you can show that the graph function exactly satisfies a quasi-linear parabolic equation. And then there's standard results which give you short-time existence. You can solve for a short time smoothly, uniquely. Okay, now, so by writing it as a graph, you more or less, you kill this diffeomorphism freedom. This is usually for Ricci flow, what you do using the Turk tricks, because you have to kill the diffeomorphism freedom. Here for mean curvature flow, the easiest way is to just write it as a graph, and that gives a canonical parametrization, and that makes it into strictly parabolic system. Okay, now, what is the avoidance? So the next important part is here we're using now codimension 1. That's the avoidance principle. So assume we have two solutions to mean curvature flow, M1T. Let's assume that they're both defined on the same time interval. See the two mean curvature flows. And we want to have that they're initially disjoint, and at least one of them, I'm not writing this explicitly, have one of them to be closed. The second one could be non-compact. So we want to have no boundary. Then the avoidance principle says, okay, if they're initially disjoint, then they stay disjoint for all times. And this is just a consequence of the strong parabolic maximum principle. The proof is in the lecture notes. Yeah. So more or less, if that is disjoint initially, then there would have to be in a first point of touching. Yeah. So these two flows have to touch the same point tangentially. Yeah. You can write them locally as a graph. And then you can use the strong maximum principle to prove that this can't be the first point of touching. Yeah? Now, similarly, you can prove that embeddedness is preserved. So if there are no self-intersections initially, then the flow will not develop self-intersections. But what you, for example, from this avoidance principle here get, we have seen, we have exactly the explicit formula for the shrinking spheres, and we see spheres shrink in finite time to a point. So if you take any hypersurface in Rn+1, you can always enclose it by a big sphere, and then that big sphere will shrink to a point. So, but this means what has been enclosed by it has to form in some sense a singularity as well. So this means we always get finite existence time. Yeah. There's also sort of a reflection of the fact that in Euclidean space, there are no compact minimal surfaces. So there's nothing to flow to actually. Now, let's do a bit more picture about singularities. This is very similar to what I guess most of you have seen for Ricci flow. No? So this is really sort of completely similar. So here's the picture of sort of this result of Huysken. Yeah? So you take something here, convex, a convex hypersurface. Yeah? Now we evolve it in time. And then this will shrink and stay convex, become rounder. Sort of, actually, it starts accelerating while it shrinks, until at the very point you get a point where it vanishes here, sort of the vanishing point. If you now would sort of magnify, we'll see later how to do this when one sort of builds, so it looks at the tangent flow. You see here the first order asymptotic of the singularity forming is actually a shrinking round sphere. Okay, so this was this picture of the singularity in the convex case, but there's already sort of a much not so. You just take, okay, it's just take the final thing, take two things which look like two spheres here, like this, and connect them with a long thin neck. And you can do this in such a way, that, for example, this initial surface is still mean convex. So the mean curvature has a sign. The mean curvature vector is always pointing inwards because you sort of this curvature is much more positive than that principal curvature in that direction. So the mean will still be positive. So the mean curvature vector will be pointing inwards. So this is still moving in one direction. I can show this is preserved by the flow. And what happens then is that sort of this neck tries to shrink, and at the same time these kind of two spheres want to shrink as well, but you can put like smaller spheres in here and you see they will be avoided. So this can't shrink away too quickly here, these two spheres on the side. So what will happen here is that something called a neck pinch is formed, and you will have seen the same picture for Ricci flow. So that you have here something like this. And here you get sort of this kind of pinching here. And if you would look here, sort of under a microscope, you would see as a first order singularity, first order expansion of the singularity, you would see a shrinking cylinder with one straight direction. So this is happening. So there are singularities. We have to understand singularities. But the problem, and so what the general hope is, okay, now the smooth description sort of breaks down, but what we would like to have, would you say, okay, we would like to continue here, say, okay, the most natural thing is sort of we do an inverse connected sum operation here in some sense. So this thing tears apart, and kind of like two teardrop shaped surfaces form after the singularity. Now these two would then both become convex after some time and shrink both away to a point. That's kind of the hope. So what you want to try to understand here in this course is sort of how one can make sense of a solution going through such a singularity when we can't describe it anymore in a smooth sense. Yeah? And the problem is in mean curvature flow, without any curvature, we want to sort of go away from curvature restrictions. So you could hope here to do surgery, but in general, even for two-dimensional surfaces, there are singularities where you can't do surgery. Surgery is sort of, there's no real hope to do that. The singularities are too difficult in their structure. So one has to come up with a different way to define a solution past the singularity. Okay, and okay, are there any questions so far? As I said, there's much more detail in the lecture notes. Yeah? So if anyone wants to have a look there, there's much more there. Okay, now as we had said before, yeah, the idea is to come up with a sort of a definition for a weak solution, especially in the end to get compactness properties, yeah? Because we all know, like from looking at PDE problems, that having compactness always is helpful to get existence and regularity and stuff like that. So to do this first, we have to understand sort of what is the natural notion of weak compactness for submanifolds. Yeah? So this would be the next part here. Huh? So just also as a remark here, huh? In preparation of these notes, I have heavily used the lecture notes of Brian White, written by Otis Chodos, yeah? And I've heavily used these because they're just extremely beautiful and sort of very nicely coming to the most essential points. So if you look at these notes, you'll see a lot of similarities there. So I don't claim any originality here. Yeah? Just saying this beforehand here. Okay, now let's first recall the natural estimate. So just to motivate this, so if you have a mean curvature flow, yeah, recall we have here this this evolution equation here of the evolving area, and we can integrate this. If we integrate this in time, you get the following estimates. We see that integral from 0 to t over mt curvature squared d mu t dt is exactly bounded from above by the initial area. So the natural energy estimate is the space-time bound on integral mean curvature. Now, if you now want to kind of understand compactness of mean curvature flows by Fatou's lemma, you could already think about, okay, you use Fatou's lemma in time. So for almost every time, you can assume you have a subsequence where integral mean curvature squared is bounded. Yeah. So the question then arises, what is the question is here? What can we say about compactness for submanifolds? Let's just make it first time independent under weak curvature bounds, weak mean curvature bounds. Okay, so this is the natural question which arises here, i.e., so what is the question? If you have a sequence mi, let's do this in any co-dimension because there's no difference here, of m submanifolds of R capital N, we want to have, now we have to at least impose some kind of area bounds. We see area bounds are something natural here, since this is monotone, so we can assume that the m-dimensional Hausdorff measure is locally finite, for all I, okay, which are compactly contained in Rn. We have locally finite m-dimensional Hausdorff measure. And now let's assume, for example, if we use here Fatou's lemma, and look at a good time here, we assume now here that mi intersected k, mean curvature squared, d mu I is less than some constant c of k for all I. Okay, that's a very natural assumption. The question is then, can we understand in what sense we can, maybe up to a subsequence, have some kind of weak convergence to some limiting object, yeah, some limiting submanifold, yeah. What is this? And the question is, what structure does M infinity have? This is like for Ricci flow if you go into metric spaces, yeah? Because then suddenly you can get compactness. Yeah? Okay. Now, this leads very natural to that definition of a varifold. Let's do this now, varifolds. Okay. Now we have, let's start off again. So we have M in Rn, an M submanifold. And so what we get a natural Radon measure. So make it very weak, yeah, by defining mu M of S, where S is just any set. It's just M-dimensional Hausdorff measure of M intersected S. Yeah? For S any subset of Rn, well, that gives us a nice measure. It's a Radon measure. If you want to integrate a function, we can also define this. It's F d mu M. It's just defined as integral over M F with respect to M-dimensional Hausdorff measure, where F is now in C0C of Rn. Yeah? So you see, this gives us a nice Radon measure. Yeah, but the nice thing is, so we have assumed area bounds, uniform area bounds, yeah, that we would get naturally. So for the Mi is above, we have, yeah, so since we have area bounds, we know these measures are locally uniformly bounded, and thus then compactness for measures gives us a limit measure. Yeah? We have up to a subsequence mu of Mi goes weakly to some limiting measure mu. But you see, now we have given up a lot of structure. We're just seeing it as a measure. The structure of being a submanifold is nearly lost. Measure is much more general, but at least we get compactness. So this is the problem. Problem is quite coarse. So we wish to refine it. Okay, now, so we don't want to really assume curvature bounds, because if we would have like bound in the second fundamental form, then we would know we can locally write it as a graph, and then at least we would get compactness, something like in C1 alpha. But that's a bit too strong. So the next thing, which is still comes sort of for free, is the following note here. Now, this is the important thing. This was all the thing what kicked off geometric measure theory. That actually a submanifold, you can't only see it as a measure as a measure on functions, but actually on functions on the Grassmann bundle. And I'll explain this. So M defines a Radon measure by using the tangent spaces on Rn cross GMN, the Grassmann bundle of unoriented M-dimensional subspaces of Rn. So over every point, we have all the M-dimensional subspaces of Rn sitting. Then we define Vm, this varifold. We define it as integral F dVm. There's sort of more or less only one way to do it. We say we take F, we take the point X, and then as the subspace of the tangent space, we just take the tangent space of the submanifold itself at that point. So this is my notation for the tangent space, and we integrate this again against the M-dimensional Hausdorff measure for F in C0C of Rn cross GMN. Okay. See, so this gives us a Radon measure actually on this Grassmann bundle. There's a little note here. You see, if you really want to have just the total area of this, or the total measure of a set S, it's just the following thing. It's HM of all points X in M, such that X and the tangent space to M at X are contained in S. Remember, S is a subset of this Grassmann bundle. You have always these components. You have the subspace component and the point in Rn. And so we, again, now this is nice. We can assume now that actually these varifolds converge to a limit varifold. So what is the idea here? So this gives us the freedom to somehow, in a weak sense, have still convergence of tangent spaces. You see here, we're keeping the information of the tangent spaces. We can still encode kind of the information about the tangent spaces just into a measure. So we can have a limit measure. So we have still, in some sense, weak convergence of the tangent spaces. And so what is also important to note, that if you take the projection of the measure of Vm onto the first component, the Rn component, this is just mu m. So we can assume that these two things are compatible. And here's the definition. An m-dimensional varifold is a Radon measure just on Rn times Gmn. Okay, and this Grassmann bundle. That's the general varifold. We have seen if we have an m-dimensional submanifold, we can always construct such a natural measure. But you see, this is much more general. This has not much structure of a submanifold still, but at least our submanifolds lie naturally in there. Are there any questions so far? Okay, so let's discuss some examples. So I'll try to see if anyone is willing to respond sort of to this, thinking about what convergence here is true and what not. There's examples of varifold convergence. This here, So let's think of this. The first thing, it's sort of always sort of as subsets of R2, Sort of we work in R2. So this is our ambient space here. Now let's look at Mn, which kind of is a subset of the unit interval. So we have here the unit interval here, just as a thing where we actually are, 0, 1 in R2. Now what are our Mn's? We take here little intervals of length 1 over 2n, and we take these n times. Now, what is the guess? What does this associated mass measure? What does this converge to? Can anyone tell me what would this converge to as you let n go to infinity? Anyone an idea? Mario, since you're there. Okay, if no one wants to respond, So it exactly converges to 1/2 times the measure along the unit interval. We just get 1/2 because we're missing always half of the total length. Okay, and what we would also have is that for the associated varifolds, V of Mn converges to 1/2 the varifold associated to the interval 0, 1. So that still works. You see, there's nice convergence of the tangent spaces. Now here's the next question. Let's do this just a little bit differently. Let's look at here little intervals instead. We just twist the intervals. We don't take so many. We turn them around. So we take these ones have height 1 over n, and we take n intervals. Anyone an idea what this converges to as measures?
probably the standard measure on.
Yeah, so it's just the interval on the whole interval. Yes, right. But do the varifolds converge? Do they converge? Anyone an idea?
Maybe it converts to the normal bundle of the unit interval.
Yes, exactly. So to the normal bundle, but if you take just the if you take the associated varifold to just the line between 0 and 1, you don't have convergence. You see, but you're right. You get a delta measure in the normal direction. Yeah, that would be the right convergence. Thank you. Okay, now here's something even weirder. Huh? Now if you have here, now it's just take as MNs. We take the diagonal. Yeah. And our MNs are we take just an approximation, like a staircase of the diagonal. So we want to refine that a bit more. We make the steps finer and finer. Now, anyone an idea what mu of Mn would converge to? Sorry.
I suppose in mass, it's going to converge to the mass of the diagonal, the smooth pattern.
But with what factor?
Oh, 1 probably.
Square root 2.
Yeah, square root of 2, right? Yeah, see, because the total length. Just think about the total length. Yeah, you get a factor of square root of 2.
Oh, yes, of course. So.
Yeah, the total length. But again, you see the tangent spaces are flipping around. Yeah? The tangent spaces don't converge to the tangent space of the diagonal. Yeah, but there doesn't exist an alpha positive such that these varifolds converge to some alpha times the varifold associated to the diagonal. Yeah, you would kind of get like 2 delta measures in 2 different directions in the E1 and E2 directions instead. But that's not anymore this varifold you want to look at. But you see, so you can sort of, with this, you at least can somehow keep track of convergence of tangent spaces in some sense as well. But you see, but you also see like in these examples here, in some sense, the curvature of these things blows up. If you think like this, if you look at these corners here, these corners have a lot of curvature. So curvature is blowing up in an integral sense, or there is already like infinite curvature sitting in there. Even if you would like to smooth it out a tiny bit, and then look at convergence. Somehow you don't have good curvature bounds. In some sense, this also motivates that if you want to have like better convergence here, where also the tangent spaces converge, you will need some kind of curvature control. In some sense, you can also think about just the functions. Tangent space convergence is something like at least C1 convergence always everywhere, or pointwise convergence of the derivative. So usually if you think about compactness theorems like Arcela-Ascoli, you need some kind of higher order control to then get convergence of a lower order quantity. So we need some curvature is like a second order quantity. So we will need some kind of weak control in a second order quantity to get some more better control, better convergence of first order quantities. Okay. The next thing we need are integral varifolds. Because in some sense, you've seen here, this converges to something in the end, which is not sort of an integer multiple of the limit. It's square root of 2. So, and then the structure gets really difficult. It turns out there is a good class where you don't have this happening, that things happen like with not integer densities in the limit. So the so-called integral varifolds. And this is sort of following what Brian White's lecture notes here. It's a very nice, very quick introduction, sort of, but still giving a clean definition. The usual definition you find in books is much more difficult. It's also important to know. But from the intuition, this is maybe a very good one. So the first little lemma is the following: let M and M prime be m-dimensional C1 submanifolds of Rn. Then we look at the following set. We look at the set Z. It's in the intersection between M and M prime, but we want to have more, and we want to ask that the tangent spaces, so where the tangent spaces are not the same. Yeah. Okay. And the statement is then the HM measure of the set Z is 0. Okay. Here's a quick proof. I'll only more or less give the proof in codimension 1, but you can reduce the higher codimension chi's to codimension 1 as well. Yeah. If M and M prime, yeah, what does this mean here? All these points in codimension 1, you have that these hypersurfaces are intersecting transversely in a neighborhood. Yeah. But then, you know, if there are hypersurfaces, then Z is an M-1 dimensional C1 submanifold by the implicit function theorem by transversality. And thus, this already gives that the HM measure is 0. In higher codimension, yeah, you can actually just use projection to a lower dimensional subspace. In higher codimension, one may show that M intersected M prime, or like, yeah, is contained in an, or let's say S subset. This is contained in an M-1 dimensional C1 submanifold by projection to a lower dimensional subspace. It's a little exercise. Okay, but this is not important. Let's at the moment mainly think about codimension 1. Yeah. So here's a little corollary of this. This is the interesting thing. Yeah. So assume you have a set S which is contained in the union of some submanifolds Mi, but it's also contained in a union of submanifolds Mi prime for Mi, Mi prime, M-dimensional submanifolds of Rn. Okay, now just take a union of submanifolds and just take any subset, and just assume this. We could extend this to a different union of submanifolds. Yeah. Now we define the tangent space T. Yeah. Define T on S. We want to say what is the tangent space to S, the M-dimensional tangent space, by saying T of X is just the tangent space of MIX, yeah, where now we just have to do one choice, yeah, where I is the first I such that X is in MI, yeah, i.e. it's just saying, okay, X is in MI without the union J less than I of MJ. Okay, so if we look at this, what we add each time, yeah, then we define T prime similarly for the other using this union here. Yeah. So what we get if we use this lemma, you see the lemma says then T of X is equal to T prime of X for almost every X in S, where almost every is with respect to the M-dimensional Hausdorff measure. So this means we can think of S being something like still M-dimensional, and the tangent space is up to 0 measure is uniquely defined still everywhere. Now let's try to set up a measure. Yeah. So thus for S a Borel subset just of a C1 submanifold. This is more or less what we've done before, huh? M in Rn, huh? We define Vs to be the varifold. So we just take one now, given by integral f dvs is just, again, f of x, tangent space mx, dhm of x, okay? And we've seen this does not depend, important, this does not depend on the choice of m by the previous bit of discussion. See, that's the beautiful thing, huh? We can take any, if you have just this S, we know it's contained in a C1 submanifold, yeah? Then we can take any other, and if it's contained in a different C1 submanifold, this definition of this varifold, because we integrate against the n-dimensional Hausdorff measure, that doesn't change. That's the same thing, it's well defined. Now this then just says, okay, what is an integral M varifold? Yeah, is now just an integral M varifold is a varifold which can be written as V is just I equal to 1 up to infinity. Yeah, so a countable union of varifolds of this form here. Still want to have it that this gives a finite measure, nice, but if we can decompose it into a countable union like that, that we call it an integral varifold. And note also, we can take sort of the same thing twice or 3 times. That gives higher multiplicity. So this means we can start counting sheets several times. We just can add sheet to sheet to sheet. Yeah? So this is then, this is a very quick definition of an integral M varifold. Yeah? Okay, and that we want to kind of treat as a generalized surface. Okay, now we wanted to introduce curvature into these varifolds. Huh?
Felix, do you have cancellation here?
No.
I mean, so you don't count the orientation?
No, no orientation. This is
okay.
Really, varifolds don't have orientation. If you want to have, if you have currents, yes, then you have orientation. But we don't add with orientation. So it's really only measures.
Okay, thanks.
Yeah. No, important, very important. Thank you. Okay, now first variation. So we somewhat at least need mean curvature, huh, of a varifold. And the first idea, is to first see if there's a different way to understand mean curvature of a smooth submanifold. Yeah? And here's sort of a bit generalized version of the smooth divergence theorem. Yeah? So assume M is a C2 submanifold of Rn. Yeah? And assume we have a vector field X in C1C. So this is a vector field of compact support, C1. Yeah? And then the idea is you define the tangential divergence. As many of you have seen that, you define the tangential divergence of this vector field at X. Just to make it really explicit here, take the sum I equal to 1 up to M. Okay, so this is the ambient covariant derivative, which is in Euclidean space, is just coordinate-wise differentiation. Yeah? Nabla EIX at the point X, scalar product with EI, or if you're in a Riemannian manifold, it would be just really the ambient covariant derivative for, you want to have E1 up to EM, an ON basis of the tangent space of M at X. Okay. And see, and up to choice of basis, of orthonormal basis, this is well defined. It's just the usual divergence. But the important thing is that we take here also the derivative in the full ambient space. Yeah? So it's not only the tangential derivative. We would only take the tangential derivative of tangent vector fields, yeah? Or if x is tangent, that just gives the usual divergence on a submanifold, as if you see it as an intrinsic manifold. Yeah? But the idea is this normal part of this vector field that gives us information about the curvature. So what you can then compute is that if you compute over M the divergence of x, now we can split this up in the normal and the tangential part. Yeah. Okay, well, this is just at each point. Now we can, this is, for example, the computation is in the notes. You can do a pointwise computation. It's very easy that for the normal part, what you get if you compute the convergence, you more or less codimension one. This is x comma nu times nu. And we know the divergence of the normal vector is like, gives the mean curvature, because you differentiate once, then you get the second fundamental form. Since we take the divergence, we take a trace, gives the mean curvature. So that's more or less the idea how this comes in. Yeah. So what you can see here, that first term gives the scalar product of x with the mean curvature vector, pointwise. But you know, for this here, there we just can use, this is just Gauss divergence theorem. Yeah? See, this is just a normal divergence theorem, Gauss theorem. Yeah? So this is just a boundary integral. Yeah? So this gives integral over the boundary of M over x comma n. This is the unit conormal, the outer dhm minus 1, yeah? Where n is the exterior unit conormal to dm. Maybe just a quick picture. I don't know, I guess it's not so usual to think about the conormal. Think of this being a hypersurface here in Rn, yeah? And then the conormal is sort of a vector which is tangent to the surface still. So here, this is the boundary, yeah? It's dm, here's m, yeah? And the conormal is still, so this is still tangent to the boundary, yeah? Tangent to m, but normal to the boundary pointing to the outside. Yeah? This is sort of the usual generalization of just an exterior unit normal. Yeah? Okay, but you see now here, yeah? What is the note here? Right. If you look at this left-hand side here, you look at this, you see the divergence here. You need to know where the tangent space is, and you need to understand the measure. So only C1 information is needed for that part. Yeah? For the measure, C1 information is enough, and the divergence, we also only need to know the tangent space at each point. So the important thing is here, yeah, the left-hand side makes sense for M merely in C1. Okay. So in some sense, this is an integration by parts. This is a divergence structure. It sees that the mean curvature has a divergence structure. Yeah? So you can kind of, here our test function is here, this vector field, we can integrate against the test function, throw one derivative onto the test function, then suddenly we need only one derivative less. So one says in the following thing, if you have a C1 submanifold, if there is a distributional vector field H, making this true, we say that H is the weak mean curvature. We sort of integrate by parts. It's like weak derivatives. Yeah? We use that the mean curvature has this structure. Yeah? Okay, but you see, this is now interesting. Yeah? So we will be able, this means like someone which has at least some kind of C1 structure, we can talk about when it has a weak mean curvature. And we have seen before that a varifold still has some kind of C1 structure because we know almost everywhere what the tangent space is. Yeah? Or at least for an integral varifold. Yeah? So for V an integral varifold, define the first variation of V by the following. You say delta V applied to a vector field X is exactly, for general varifold, you just say div T of X against dV little x, sorry, this is little x and T, yeah? So that's the capital X and little x. Or if you're an integral varifold, you can just write this as, you know what the tangent space is almost everywhere is dV at the little point x applied to capital X d mu V of x. Okay. So this is the first variation, and here's the remark. Why is this called first variation? Yeah. If you have a, for example, a vector field C1C, compact support in Rn, then we know we can construct a one parameter family of diffeomorphisms from this vector field, where we just say, okay, phi 0 is the identity, and we want to have ddt of phi t is V composed with phi t, yeah? Just so that this is the flow along the vector field, yeah? Then you can compute if you have an integral varifold, so you need an integral varifold for that, yeah? That you can define something which is sort of, you move this varifold, more or less you move all these submanifolds which we used before to find the integral varifold, you move them by this diffeomorphism applied to K. Now you take this as the local mass measure, yeah? You take the first variation of this, yeah? T equal to 0, then you exactly get delta V of X. We assume that the support of this vector field X is compactly contained in K, and that's compactly contained in Rn. I guess that's just the first variation of area. What is the note here? Yeah? But you see again here, the first variation only needs C1 information, especially if we have varifold conversions. This will be continuous under varifold convergence, yeah? Because if the measures as measures on the Grassmann bundle converge, this will converge because it's just a function. Yeah? So if Vi as varifolds converge to a limiting varifold V, then we have that delta Vi of X converges to delta V of X. So this is exactly the reconvergence of the first variation. Huh? Okay, now what do we assume? Assume we have local bounds on the first variation. So what does this mean? Huh? Want to have delta V applied to X is less than a constant C of K times the L infinity norm of X. X is our vector field. Yeah? For when we have the support of the vector field is contained in K, is compactly contained in Rn. Yeah? So this is locally, this is called when you have local bounds on the first variation. But what you see here, yeah, so we have seen, so this is not only defined for C1 vector fields, but this bound here allows us to extend it to C0 vector fields just by approximation. Huh? And we know now we have a continuous linear functional on continuous function, linear functional on linear functions, then we can use Riesz representation theorem and represent this by a measure. Huh? So we can apply the Riesz representation theorem. It gives, there exists a Radon measure, a vector valued one, so lambda, we'll split it up, lambda and a lambda measurable unit vector field capital lambda, such that the following is true, that you can write delta V of X is just X scalar product with lambda integrated against this measure d lambda. It's just the Riesz representation theorem. Okay, now what we do now is we decompose lambda with respect to mu v. This we have. We know we can differentiate sort of this measure lambda with respect to mu v. So then there's the absolutely continuous part of this measure and the singular part. And now what we can do, we can write now delta v of x as x times lambda times the absolutely continuous part plus lambda times the singular part. Now, what means the absolutely continuous part? I mean, we can use the density of the absolutely continuous part with respect to the mu v to write this as x lambda times, this is the density. This is exactly the how you can define the absolutely continuous part. So this then we define as just minus mean curvature vector here. And then this here we write as here x comma lambda d lambda singular, where this is exactly, we say, okay, this part here is the exterior unit normal at these points. Okay, so what do we get here? We can, if we have a bounded first variation, we can write our first variation exactly in the form how we have seen it before. X comma mean curvature vector d mu v plus x comma exterior unit normal d lambda singular. So this is more or less the boundary measure, and this gives us the mean curvature. Okay, so this means we even in general have such a structure theorem if we have bounded first variation. And so the important theorem is here is Allard's compactness theorem. For integral varifolds. So the assumption is, suppose we have vi converging to v is a sequence of integral varifolds. We can, for example, assume they have uniform mass bounds, so we can extract a subsequent which converges weakly to a varifold v. But this limiting varifold can be very weird. This could be distributed everywhere, smeared out, doesn't look anymore at all like a submanifold. If now the statement is the following: if the vi have locally uniformly bounded first variation, i.e., if we have a compact subset of Rn, there is a constant C of k, which is independent of I, such that if you have a vector field in C1c of Rn with support the vector field in K, then we have, it's exactly just saying what we said before. This is just the local uniform first variation across the sequence, C of K times X in the infinity norm. Then the statement is, then the limit V is also an integral varifold. So this means, this kind of, we'll see, so let me do a little remarks and we can discuss this, so don't say things double. So what we trivially obtain, remember, first variation was continuous under weak convergence, so we trivially obtain that delta V of x is also this, the limit ck times x. So the limit has, in the above sense which we wrote down here, it has the weak mean curvature and singular part. then if you take something smooth, this is maybe the important thing, a sequence of smooth, or what means smooth is just C2, submanifolds satisfies the hypothesis of Alazim. So I assume it's already converging weakly as a variable to limit. If and only if. See, what do we want to have is we just need that the mean curvature is bounded in L1 locally. And we want to have a locally finite boundary measure. So you see, this is the interesting thing. So you see, more or less to get a good structure of our limit, we need an L1 bound on the mean curvature plus finite boundary measure. Then we can make sure that our limiting object still really looks like kind of finitely many sheets. We still can somehow make sense of the limiting actually being an m-dimensional submanifold. Where, so here, sorry, where the sigma I is the boundary measure. Of the MI. Okay. Any questions regarding this?
I can ask a question from chat, which is after you defined the first variation, you gave motivation using these flows, and I suppose the flows should be associated to X instead of B. I think you just...
Yeah, maybe didn't I write this? Did I make a mistake there?
I think you associated everything.
Oh yeah, sorry, that was a mistake. That's just a typo. Writing too quickly. Yeah. Okay, thank you. Sure, they can't be associated to V. That doesn't work. Thank you.
Okay, and maybe another question more on the content. Is there a good example that the number of components can go both up and down in these limiting processes, or sheets? I think you call them.
So you can the number. What do you mean by sheets going up? Is you can just have two sheets coming together, and then you have to have something counted double in the limit. You see, if you have like just two parallel planes, which converge to the same parallel plane to the same plane, then the limit has to be counted double. You see? So the picture here would be the following, yeah. It's very simple. You just take two lines, yeah, with like where the distance here is epsilon, or let's say 1 over n, yeah. And they will converge, yeah, in the end to a line. But you see, from the measure, this here has counted. The limit has to be counted twice. Otherwise, you don't have mass conversions.
Okay.
Yeah. So yeah. So it's you have no cancellation. Yeah. So you have no orientation, but you have to count the limit twice. Does this help?
Yes. Yes. Thank you. Thanks.
Okay. Now, yeah, very good question. Here is now one other thing, but something weirder things can happen actually as this here. Yeah. So the quantities actually of the L1 norm of the mean curvature, yeah, and the sigma, the boundary measure, they can be mixed up in the limit. Here's an example, the first one. Okay, it's very close to what we just discussed. Yeah, take a very long two parallel lines and cap them off. Yeah. Now we can make them even closer. And in the end, this converges to something. Here, just this is counted twice, huh? But you see, this has no boundary. This is also no boundary, but this has boundary. And you see here, there's a lot of curvature sitting here, in these circles. And this curvature concentrates in the end to the boundary measure. Yeah. So this means they can transfer between each other. Here's something else, even simpler, or not simpler. So just take it a round circle. Okay. Now you take here the following, just take a polygon inscribed in a circle. Now you refine the polygon. Finer and finer. Until in the end this converges just to the circle. And so you see here you have boundary, but no curvature for these two, and you have no boundary, but curvature. So it can go both ways. So it's interesting. So this can happen. But you still get a nice structure in the limit, you see? The limit is still an integral varifold here. Okay, now let me use the last 15 minutes to at least give you the definition of a Brakke flow. And you see why we need all this terminology. Yeah. Here are the Brakke flows. Okay, so here's the definition. And I will mostly do n-dimensional Brakke flows in Rn+1. This works in any codimension, but just to make it a bit clear from the notation. An n-dimensional integral Brakke flow in Rn+1 is a one parameter. This is more or less weak mean curvature flow, yeah? Family of radon measures. So we first forget all structure of submanifolds, yeah, that we has did before. Yeah? So it's just radon measures over an interval I subset of R, such that. So what do we want to have? Yeah, for almost all T and I, there exists an integral and varifold V of t, with mu of t is the associated mass measure to this varifold. Yeah, so this means for almost every time our radon measures actually come from varifolds. Yeah, we can actually prove this is the mass measure uniquely defines the varifold. Yeah, and we want to have a bit more, such that V of t has locally bounded first variation and has mean curvature, weak mean curvature, has weak mean curvature. H orthogonal to the tangent space TV of t almost everywhere. This is not necessary to almost everywhere. Not necessary to include this, this orthogonality. It's just easier. There's a deep theorem of Brakke which proves that this is true for integral varifolds, but it's easier to just put it into the definition. So you'll see what this assumption also means is, you'll see in a moment, that we also don't want to have a singular part of the mean curvature. There's only we want to have that the first variation is actually absolutely continuous with respect to the mass measure. So this is part of the statement here too, yeah. For a bounded interval T1, T2 in I. So more or less our mean curvatures, for almost every time there's no boundary. Huh? And any compact set K in Rn+1, we want to have that the integral T1 to T2 over k over 1 plus mean curvature vector squared d mu t dt, but this is finite. Yeah, and sort of part of this statement means here, yeah, you can write this explicitly, that we want to have no singular part of the first variation, only the part which is absolutely continuous with respect to the measure d mu t. And 3 is if, now this is not yet saying it's mean curvature flow in any way, yeah. If t1 and t2 this interval is contained in I, yeah, and we have a test function in C1c. Now we want to have it time dependent, n plus 1 cross t1, t2. Yeah. Then with f positive, then we want to have that the integral over t2 d mu t2 minus integral f t1 d mu t1 is less or equal t1 t2 integral now minus mean curvature squared f, I'll write it like this, plus mean curvature vector scalar product with gradient f. This is the ambient gradient, yeah? It's an ambient function, plus df by dt, brackets here, times d mu of t dt. So this is the whole definition. And this is more or less an integrated version of mean curvature flow. And let's see why is this the case. So this is more our defining equation. Here's the remark, yeah. If mt, let's say t in t1, t2, is a smooth mean curvature flow, then we can just compute this more or less the same as this first variation formula, just with this function f inside, yeah. So what you get here, so you get the first thing, which is just you vary the measure, so you get mean curvature squared times f. Then plus, then you get this term where you have to differentiate f in space. And then you get as the speed vector the mean curvature, and you have to differentiate f in time, dA. Huh? So you see that this equation here is an integrated version of this equation with one difference. We have this inequality here. Usually you would expect that there's an equality. Yeah. So here's the question. Yeah. So why do we only require the inequality? 3. So this is now here's the question to you. Has anyone an idea why one needs this inequality here? Why you can't work with an equality? It's not such a trivial question.
I suppose if you want to, like if the plan is that this thing passes through singularities, then it has to do something which is like something akin to surgery, and in surgery you usually have some losses.
That's one way. It's more prevalent if you want to have compactness. And why that? So I guess you have seen like functions with weak derivatives. Yeah? Like if you assume you have a function in W12, a sequence of function in W12, let's say with where the gradient is bounded, uniformly bounded in L2. What do you know about the limit? The norm of the limit. You get a weak limit. What do you know about the norm of the weak limit? So here's the example, yeah. So example is assume, let's say, fi are in W1 to 0 of omega, huh? You want to have integral over dfi norm squared dx is less than c. Yeah. Now we know by weak compactness, I can assume that fi goes weakly to f infinity. Huh? What do we know about the Dirichlet energy of the limit?
It should be bounded by the lim is inferior of the
Exactly. So we know that,
norms of the
but it is only be bounded, yeah, is less or equal lim inf. Huh? But you see, there's no continuity that can jump down in the limit. Yeah. Here's an easy example. Just take these functions here. Yeah? Take, for example, functions like a zigzag function, yeah, which approximates the zero function, the gradient. Yeah. See, you have oscillations. Yeah. So, and we have seen before the mean curvature is in some sense converging weakly to the limit. Remember, the first variation is converging weakly. Yeah? So the problem is that that we only have weak convergence of the first variation to the limit, but we don't get better convergence. So this means the L2 norm of the mean curvature can jump down in the limit if we want to get compactness. Yeah? And if you see, if we integrate this here and want to have equality, then in the limit, this might jump down. It might be too small in the limit to get equality. If this is too small, to compensate for that, we have to allow you for the inequality. That's the idea. Yeah? To make it possible that we get compactness, this is what we want. We have to allow for this inequality. Yeah? So that's the idea. And it comes exactly from this idea that when you just think about weak convergence of functions. Yeah?
May I ask which limit are you taking in this definition? You're speaking about semi-continuity, but which parameter is taken to the limit?
Okay, so let's think later. We have a sequence of Brakke flow of mean. Just take smooth mean curvature flows. Yeah?
Okay. Yeah. So the Brakke flow is supposed to be the limit itself.
Yes. Or you can even take Brakke flows, but even easier, take smooth mean curvature flows. Yeah. Yeah. Assume we have proven, we want to prove compactness. We want to say, okay, this class of Brakke flows is weak enough, so we get compactness just more or less under area bounds. So we have seen before for this, if you take convergence as varifolds, we have seen that sort of the first variation only converges weakly, but not better. So in some sense, the mean curvature converges as kind of like under weak convergence by integrating against the test function and putting the derivative on there. So this means in the limit, our L2 norm of the mean curvature can still jump down. Is this clearer, Mario?
Yes, thank you. So f is the test function here, and you're integrating again.
F, or more or less, you think of this here, what we did before here. Yeah, f is a test function, or you think what we did here. Yeah, we see. Okay, we say okay here. Here. Yeah, here this you see that the delta vi in this Allard regularity theorem. Yeah, you see this delta vi. This is continuous. See, where did we define it here? You see, this is if you have a varifold converging to a limit. See, this is always converging for every fixed x. But if you take the definition of the weak mean curvature, if these have weak mean curvatures, yeah, this more or less says that the mean curvature is only converging weakly by integrating against the test vector field. See, but there could be oscillations which are killed out in the limit. Yeah.
Yeah, thank you.
Yeah, no, but yeah, it's very important. This is a very good question. Yeah. Yeah. Are there any other questions? Okay, if not, then I guess I'll stop here now, and we continue tomorrow. I'll share another link tomorrow morning, or I'll put this into this Dropbox folder. So if anyone wants to access these notes, you can access these notes as well.
Okay, thank you, Felix. So are there any questions in the room?
Yeah, any other questions?
They look all tired.
Yeah, I know.
Okay, thanks, Felix. So
Okay.
we'll meet again tomorrow, same time, right?
Okay.
Bye-bye.
Bye. Thank you.
Moi aussi. J'ai conseillé, moi.
J'ai envoyé ça.
Ça me carré.
Je peux envoyer à Fanny, peut-être.
Ouais.